Welcome to this lesson on variables, fair tests and causation. In this lesson we'll try to develop our understanding and skills needed to effectively design an experiment that achieves a fair test that can prove causation. You'll need to have handy paper and a pen to make notes and a scientific calculator to perform calculations. Throughout this video you can of course pause and rewind at any time, though at specific times I do ask you to pause the video and complete a task. Please make sure you do, as this will significantly aid your learning and result in good use of your time. So to start this lesson, I would expect you to know what a hypothesis is, how variables are different from experimental methods or equipment, and basic ideas about a fair test. If you're unsure about these last 2 points, then I recommend you review these ideas before continuing on with this lesson. So before we begin with the lesson, I would like you to take a few moments to answer these questions here. Pause the video and restart when you are ready. So here are the answers to the first question. Aims are general statements describing what our experiment is trying to find out, whereas hypotheses are statements that state the relationship that we expect as stated by the theory. A hypothesis at the end of an experiment will either be proven true or false. Then the answers to the second two here. Fair tests must have all variables except for one kept the same. The one that is going to be changed is the independent variable. The last question here, I've included this because I often find that students incorrectly associate using the same piece of equipment as a control variable. Well, this is not the case, as will be explained later on. If you didn't quite get that last question correct, don't worry, as I will cover that later on in the lesson. So let's take a further look at aims, hypotheses and variables. So aims are general statements that describe the purpose of our investigation. Let's say we want to investigate how the frequency of a wave on a string can be adjusted by varying the length of a string. That would be the aim of an experiment. A hypothesis then is a statement that is made at the start of an investigation and clearly states the relationship between variables as stated by the theory. So we must understand the scientific theory in order to do this. And here we recognize that many investigations we undertake are used to confirm and incrementally improve science rather than make groundbreaking discoveries. So in the case of the frequency of a wave, we may say that the frequency of a wave may increase in proportion to the square root of the tension applied to the string. That is what the first harmonic frequency equation tells us would be the case. And then lastly, the variables. Once we've got a clear relationship proposed through the hypothesis, the variables can be identified, and these will be the things that can be measured, the things that can be adjusted that are in the hypothesis. So in any experiment, the experimenter seeks to change or manipulate the independent variable, and the experimenter will then record the subsequent effect on the dependent variable. To determine causation, that is, that the change of the independent variable has actually affected the dependent variable and how it has affected the dependent variable. So to determine that causation, it's crucial that there is only one variable that changes. And so all other variables that could affect the dependent variable should remain constant. And this is to show that the experimenter can be confident the cause of the effect on the dependent variable was the independent variable, and the independent variable alone. That is what makes a fair test, and thus can be used to prove causation. Fortunately, physicists can more often than not refer to an equation to identify not just how we expect the independent variable to be related to each other, but also what the key control variables will be, because they will be the other factors within the equation that we should keep the same. So, in summary, the independent variable is changed or perhaps chosen or manipulated in some way. With the dependent variable we record the effect, and the control variables remain constant. I'll invite you just to take a moment to pause the video and make some key notes on this and the previous slide. So let's look at an example from Year 12 Physics. Hopefully this is an experiment that you remember, looking at standing waves. In this activity we're going to look at making sure we can identify what the variables are, and it's important you're able to clearly understand this, as there's usually a writer method type question in the A2 exam series, and in the response to this question a clear understanding of the different variables needs to be clearly communicated. So let's say our aim was to investigate how the frequency of a standing wave is affected by the mass per unit length of the string. With this experiment we could have looked at a number of other factors, and we will look at some of those later on. So from this we must then derive the hypothesis, and we're going to have to get that from theory. So in this case the equation for the first harmonic leads to a hypothesis that the frequency of the wave will be inversely proportional to the square root of the mass per unit length. From here we then identify our variables. The independent variable, that is what we are going to adjust, what we're going to manipulate or choose, is the mass per unit length. This is the factor doing the affecting as seen in the aim, and we would do that here by either using different strings or by doubling up our string on the wave. The dependent variable here is the frequency. This is how the whatever is affected by bit of the aim. The control variables then here will be tension and length, and we choose those because those are the other two factors within the equation that we are not adjusting or measuring, and so we must keep these the same. Now, a word of caution here: we should be cautious not to overindulge ourselves with extra erroneous control variables, by bringing in ideas about perhaps the measuring equipment we're using, or the temperature of the room and things like that. But we should also make sure we cover anything that we know might have an effect on the experiment that's not explicitly referred to in the equation. Now here is where a good understanding of physics aids good experiments, and why good investigations usually confirm and develop science rather than make unexpected discoveries. As I've mentioned, one thing to avoid is listing measuring equipment or methods or even people as control variables. This should be the case unless the equipment can have an effect. So rulers and timers and thermometers, they aren't going to affect the value of a measurement, though they may of course affect the resolution of it. At clamp stands, they've got no effect whatsoever, though if there are moving parts such as a bearing, then this may need consideration. In this particular example, in the traditional way of doing the standing wave itself is horizontal, and there is a pulley with the string running across it and masses hanging off it, that pulley may have friction, and so that friction, the static friction that's in the pulley, may reduce the tension that we expect there to be from the weights. And so we do need to either make sure we're always using the same pulley, or we make sure the pulley is suitably lubricated such that there is minimal friction in it. So again, pause the video briefly here and take some notes should you need to, and then we'll move on and have a look at another example. So here is a second look at this sort of experiment, but we're going to change the aim here. The aim now is to investigate how the frequency of a first order harmonic standing wave is affected by the length of the string. We've got a hypothesis stated there, so what I'd like you to do is determine what the different variables would be. Pause the video and restart when ready. So hopefully you have no problem in getting these variables here, the independent variable being the length of the string, the dependent variable being the frequency, and the control variables then is the tension and mass per unit length. If you've included in there the friction in the pulley, that's fine as well. Here is a third example of this type of experiment, but again with another different aim. We're now looking at how the tension needed to achieve a first harmonic standing wave is affected by the mass per unit length of the string. Again, here I'd like you to write a hypothesis, and that's where you need to refer to the equation. It's going to need some rearranging to do that, and then also think about what the different variables will be. Pause the video and then restart when ready. So a hypothesis here, which is derived from the equation, will be the tension of the string will be proportional to the mass per unit length. When determining how one variable affects the other from an equation, variables will always be proportional to each other if they can be written as a fraction, as a numerator over a denominator. The variables then are here. The independent variable is the mass per unit length because that's what we're going to choose. We're going to change that. The dependent variable will be the tension, and then we've got our remaining variables there which we're going to keep the same as our control variables. So here are three further experimental aims similar to those you will have come across in Year 12 Physics. What I'd like you to do is to write a hypothesis associated with each aim. You will need, of course, to refer to any equations or theory behind these. And then I'd like you to write the variables that would be needed to prove the causation stated in the hypothesis with a fair test. Pause the video, and then when you're ready, unpause and compare your answers to the given answers. Don't forget, you are going to need to refer to the theory behind each experiment, and specifically the relevant formula to determine the correct approach. Pause now and continue when you're ready. Here are the answers for the Young's modulus experiment. Do compare these obviously with what you have written, and hopefully you've got the same ones as me. Here are the answers to the potential divider experiment. Note with our hypothesis here, we can't say that the potential difference and the resistance are directly proportional. And the reason is because within a potential divider there is a fixed value of resistance in the second resistor, and so the overall resistance of the two potential dividers is not a fixed value. As one of the resistors increases in resistance, so does the overall resistance, and therefore the current will not be constant through the potential divider. If there was a constant current through the potential divider, then potential difference and resistance would be proportional to each other. And then lastly, here are the answers to the third aim about interference patterns, and hopefully you have no problem achieving this. I hope this lesson has been helpful to you, and I look forward to helping you in the next lesson.